Good morning. All right, so it's 8 o'clock. We'll get started here. Okay, so I'll show you where we are in the course. So today we're dealing with some nuclear chemistry, radioactivity and such. There is an essay question associated with test 4 as well as a units quiz. So make sure you're aware of those. Those can be done anytime, and you probably should get on them earlier rather than later. The notes about the essay question are here in the test 4 folder, and you can read about those details. Take a look at them. If you have any questions, let me know. We can talk about them during another class before test 4 is due. Okay, let's get on to what we're talking about today. And today we're talking about nuclear reactions. Make this a little bit bigger here. Good. So first of all, we're going to be talking about the nuclear processes and energy. Now, one thing you probably have heard of E equals mc squared. That's the familiar Einstein formula that links energy and mass together. So E is energy, m is mass, c is the speed of light, and that ends up being squared. So it's a pretty big number. The speed of light is a big number. And the energy is measured in joules, and the base units are kilogram meters squared per second squared. So mass is in kilograms. Speed of light is meters per second, but that's squared, so it's meters squared per second squared. But that whole entire unit is actually a joule. So the nuclear processes we're going to be talking about are going to result in a mass defect. That is, there's a mass lost during the nuclear process, and this mass ends up being converted into energy. So this is an example of a fusion process where we've taken two elements and then joined them together, and we're forming from this hydrogen 2, which is also called deuterium, and this hydrogen 3, which is also called tritium. These are joined together, we get helium and a neutron. Now, overall, you can see 2 plus 3 is 5 and 4 plus 1 is 5. The thing is, though, that these masses are actually resulting in something that overall weighs less than what we started with. So what we can talk about here is a concept known as mass defect. So there's a loss of mass during this process, and that mass ends up being converted into energy. The mass defect formula is the sum of the mass of products minus the sum of the mass of reactants. And these masses are measured in what we call atomic mass units, or AMU. So you can see here, it's not a very difficult equation to figure out mass defect. We add up everything that's on the product side, we subtract everything that's on the reactant side, and we end up getting a negative value. Now, the reason for that is because mass has been lost in going from the reactants to the products. It's this mass that ends up being converted into energy. So the figures we'll need for that are a conversion that allows us to get AMU into kilograms, and that's what we have here. As you can see, 1 AMU is not a very big number, 1.6605 times 10 to the negative 27 kilograms. We need Avogadro's number so we can figure out the per mole of something. And we've got the speed of light here, 2.998 times 10 to the 8th meters per second, as I said, quite a big number. Does anybody have any questions so far? I will explain these numbers up here, the 2 and the 3. Suffice to say they are isotopes, and isotopes are compounds or elements where they have the same number of protons but different numbers of neutrons, and we'll get into that later. These are still one proton species, but this one has 1 neutron and this one has 2 neutrons. We'll get into that in a little bit. But as it is, I just want you to focus here on the mass defect. All right, how do you feel so far about this? Just ignore the last option here. How do you feel so far? 5, 4, 3, 2, 1. Okay. Can I get some questions here? So there's 3 of you who understand halfway. Any questions? Okay. So in order to solve the amount of energy, what we need to do is use our formula here, E equals mc squared. Now the mass is negative 0.020207 AMU. That was from the mass defect. You'll notice there was a negative out the front, but we're looking for the energy actually released. So we don't really worry about the negative sign here because we're looking for a positive value essentially of the energy released. You could leave a negative out the front, which would indicate that that energy was released at the end, but generally we just ignore the negative sign and continue with the math here. So we need to convert that into kilograms. So I used the conversion factor I showed you earlier, not something you have to memorize. And then multiply it by the speed of light, which is squared. So that whole thing ends up being squared. And then that whole thing ends up having the unit of joules. So it's kilograms meters squared per second squared, which is a joule. The joules cancel, we're left with kilojoules at the end. So this allows us to get to kilojoules. If we want kilojoules per mole, we multiply it by Avogadro's number, which is 6.022 times 10 to the 23. And the unit on Avogadro's number is moles to the negative 1. So it's objects per mole or something per mole as being the number for Avogadro's number. So we end up getting 1.86 times 10 to the 9th kilojoules per mole. So that's a pretty big number. When you consider that most chemical processes, you'd be lucky to get maybe 200 kilojoules per mole out of a chemical process, you can see that 1.86 times 10 to the 9th kilojoules per mole is pretty big compared to what we might get from a chemical process. This is why processes like fusion are so attractive, because they create large amounts of energy from very small amounts of material, much smaller amounts of material than any chemical processes that we know of. The problem is getting these 2 things to actually interact and join together. That takes a lot of energy in and of itself, and self-sustaining fusion is something that we have yet to be able to properly achieve. So it has been achieved for small amounts of time, but it hasn't been achieved for very long. But at some point, research is underway into how to possibly get these things to interact and be a self-sustaining process and use up less energy than it actually creates. All right, how do you feel about the E equals mc squared and the equation we've got so far? How do you feel about it so far? 5, 4, 3, 2. Okay. So we're pretty good with that.
Can I ask a quick question?
Yes.
So for mass defect, will we be given the mass for each element?
Oh,
or...
yeah. You can't do it otherwise.
Okay, all right, thank you.
Yeah, you'll always be given that. So that one's not too difficult, is it? Now, the other thing, the next thing I'm going to talk about here is calculations relating to half-life. So nuclear decay is a first-order process. It's bound by equations that we talked about back in test 1. And that is this kind of rate equation, rate equals Ka. So the rate of reaction is directly proportionate to the concentration of the reactant, that is A to the power of 1. We can calculate an integrated rate law based on that, and you can see that's it there. And we can also get a half-life. Now, the interesting thing about the half-life is that this is 0.693. This is actually the natural log of 2. So it's log 2 over K, essentially. The interesting thing about the half-life of a first-order process is that it doesn't depend on the initial amount of material. So we always talk about half-lives of nuclear reactions or nuclear or radioactive substances. So, for example, the half-life of strontium, I can't remember the mass of that one. But there's an isotope, a radioactive isotope of strontium. I can't remember the exact mass of it, but it has a half-life of about 30 days. So what that means is that after 30 days, there's half of it left from what there was in the beginning. But it doesn't matter how much there was. So let's say there was a kilogram. In 30 days, there's half a kilogram. If there was 10 kilograms in 30 days, there'd be 5 kilograms. So it all depends on how much there is at the beginning as to what you get left at the end. But the equation actually doesn't include how much there was at the beginning. As you can see, there's no mention of A0 or the starting amount of the material that we're talking about. So what this means is that if we've got a half-life, we can easily get this rate constant K just by using this equation. We don't need to know how much we're actually starting with. However, what we can do is we can use this to calculate times, and we can use it to calculate the time required for a certain percentage of a sample of a radioactive element to decay or to remain. So this is a very useful question for us. I mean, when we're talking about radioactive waste, for example, it's very important to us to know how long it's going to take for that radioactive waste to decay. Obviously, the longer the half-life, the longer it's going to take to decay. And we know that radioactive materials are quite dangerous, so we like to know how long it's going to take for them to go away. So if you were asked a question, for example, with this one, this is plutonium-240, and we're given a half-life here, 6,580 years. We want to know how long it would take for 95.00% of that sample to decay. So given the half-life, we can calculate a K value, and we could also take this integrated rate law. I'm not going to do the math on it, but we can rearrange this a bit, and we can come up with an equation here where it's negative KT is equal to natural log of A over A0. Now the K is the value we're going to calculate first based on the half-life. And then the A is the amount we have of A remaining, and A0 is what we started with. What that means is that A over A0 represents the fraction remaining when the time equals T. So this is a fraction. What we have over what we started with. So think of a pizza. If a pizza's half eaten, it's what's left of the pizza divided by what was there in the pizza at the beginning. So A over A0 is the fraction left after the time has passed. So the first thing we do is we find K. Now K is found by rearranging this half-life equation that I showed you earlier. I explained that this 0.693 is log 2, a natural log of 2. If you put natural log of 2 in your calculator, that's what you come up with. So T half is log 2 over K, so K is equal to log 2 over T half. So we take the log 2, divide it by the half-life, which is given in the equation, and we get K, which is a rate constant, which is measured in the unit here of years to the -1. So it's always going to be whatever unit you have on the half-life, but to the -1. So it's per year, essentially, is what this rate constant actually ends up being. The other equation we have in order to actually work out the fraction, so that we can work out the time with the fraction remaining, is we can use negative kt is equal to natural log of a over a0. So t is equal to negative log a over a0 over k. So we're just taking the k over the other side here and the negative over here as well. In this part, a over a0 represents what's remaining, but look at the question and look at the wording of it. It says 95.00% of a sample to decay. So if 95.00% has decayed, that has gone away, then 5.00% must be what's remaining. And if we take 5.00% and convert it into a decimal, this is what we get, 0.0500. So that becomes the fraction remaining is going to be 0.0500. So that gets substituted in for a over a0, and we end up calculating a time here, which is 28,500 years. So why does this make sense? Well, it makes sense because we know that the half-life is 6,580 years. That's how long it takes for 50% to decay. We expect that to get 95% to decay, it's going to take a whole lot longer than 6,580 years. And this is what we end up with. So 28,500 years for plutonium-240 to decay to 5% of what it was, or to decay to 95%. So to decay 95%. So the wording here is very important. We need to be sure that we read this properly. This is to decay. And if we look at the question and change the wording to remain here, and this would be the time required for 95% to remain, that means only 5% has decayed. We would do exactly the same math, except that when we get to a over a0, the amount remaining is what it says in the question, which is 0.9500. And we do the math here, it comes out to be 489 years. So if 6,580 years represents the time it takes for half of it to decay, then the 489 years is expected for only 5% of it to decay. It's just going to be a lot less than 6,580 years. All right. Let's see, how do people feel about this question so far? Five, 4, 3, 2, 1. Some people don't want to vote. Okay. All right. Any questions then? I mean, we just do have a few people here who are understanding it halfway. What's your question? Remember, decay was found up here in this part of the problem after we got the half-life. And then that gets substituted down in here. And you can see the per year is on the bottom, then it becomes years when we do the math here. Does anybody have any questions? Okay. All right. I'll show you the test questions in a bit, but they're very similar to what we're looking at here. Same with the mass defect question as well. That's going to be on the test too. But I will show you those in a little bit once we get through some more of these problems. All right, so what we're going to be talking about now are modes of nuclear decay. And what we're discussing here are the different ways that nuclear decay can occur. We're going to discuss these 5. We've got alpha decay, we've got beta minus decay, beta plus decay, K electron capture, and gamma decay. So these are all ways that radioactive materials can decay. All right, so let's talk about, first of all, what's going on with the periodic table. So I need to pull up a periodic table here. I wonder if there's one in test 4. There may not be. Let me go back to, actually I'll just find one on the internet, I guess. Actually, what I'll do, I will open up my courses here, and I'll go to the test. That'll be a better idea. I'll leave that open. Okay, let's see, ungraded copy of test 4. Preview, start quiz. Okay. All right, so here's our periodic table. And this is what we notice about the periodic table if we're looking at the masses. You'll notice that as we go up on the periodic table, up for the first 20 elements or so, you'll notice that the atomic number and the mass number are comparable. In other words, I can say for up to 20, that the mass number is about double the number of for the atomic number. So let's first of all make sure that we understand what we mean by mass number and atomic number. So the atomic number is the number that's on top, generally speaking, and the mass number is the one on the bottom. Now the atomic number, I think we're all aware of this, is equal to the number of protons, whereas the mass number is equal to the number of protons plus the number of neutrons. So that's meant to be a hash there. It doesn't look like a very good hash, but it's a hash. So the number of protons plus the number of neutrons. What that means is the number of neutrons then can be easily obtained by taking the mass number and subtracting out the atomic number or the number of protons. So if you look at everything up to 20, what that means is let's say we look at calcium, you'll see that the atomic number is 20 and the mass number is 40, which also means that the number of protons is going to be 20 as well. 20 plus 20 is 40. But what you might be confused about here is why we don't get a whole number on the mass number. And the reason for that is because of isotopes. So as I said earlier, isotopes have the same number of protons but different number of neutrons. So a different number of neutrons. So for example, with hydrogen, for example, we have 1H, which has 0 neutrons on it. And it weighs 1, right? So this is for the mass number. 2H, which is deuterium, has 1 neutron and it weighs 2. And then we've got tritium, which has 2 neutrons and 1 proton and it weighs 3. So all these have 1 proton, but they have different numbers of neutrons. Now for water, so for hydrogen, it makes up about 99.923%, something like that. Then you've got tritium, which makes up 0.008% or something like that. And then tritium, which makes up 0.00005% or something like that. So tritium is the radioactive version of hydrogen, and it's not very common. But what we do here is all of these natural abundances here get factored in, and the atomic mass that appears on the periodic table is then based on all of these isotopes, and then they're all weighted for their natural abundance. So the mass for hydrogen here is 1.00794, which is pretty close to 1, because 1 is by far the most common of all of these. But it's not a given that one will be very much more common than the other. Take a look at chlorine, 35.4527. This is because 2/3 of all chlorine weighs 35. The other third weighs 37. So you can see it comes out to pretty close to 35.4527, closer to 35, but still significantly different from 35 because 1/3 of all chlorines are chlorine 37. All right, how do you all feel about isotopes? How do you all feel about isotopes? Should have seen this before at some point, I'm sure. All right, 5, 4, 3, 2, 1. I don't know why we're still getting 2 people not voting. All right, does anybody have any questions about the isotopes? 2 people that understand this halfway, so do you have questions? Any questions about isotopes? All right. So my point here has to do with how many protons there are versus how many neutrons. So let me get back to my initial discussion here. So if you look at this little graph here, it's kind of interesting. This line here represents a 1-to-1 proton to neutron ratio. So as you can see, going from 0 to 20, you can see that pretty much most stable elements pretty much follow this line. Not exactly, but pretty much follow this line. So these dots here represent stable isotopes. So these are non-radioactive isotopes. So they all go here. And we have this band of stability, right? And then this is where we can expect to see this is also where we can expect to see radioactive materials as well. So they are going to be above and below this line of stability, so-called, or stability band. So we've got this 1-to-1 ratio, and you can see that initially, yeah, that's what we're going to find. They pretty much follow that. But look, take a close look at the periodic table. And what you'll notice is that as we proceed past 20, take a look at, say, even bromine over here. So bromine is 79.904. Now it's 35, which means that if we're talking about it being 80, so there must be 45 neutrons. If we're talking about bromine 80 as being the main component of bromine. So we've got 35 protons, 45 neutrons. So you actually can see there's more neutrons than protons. And you can see that that's something that sort of proceeds as we as we go up the periodic table and we get further and further from a 1-to-1 neutron ratio, proton to neutron ratio. So why would this be? Well, you've got to consider what the nucleus is. Now, the nucleus is all protons. What holds the protons together in the nucleus is something called strong nuclear force, which is something that only becomes apparent once we get two protons or neutrons very close to each other. So if they're incredibly close, incredibly packed together, then they will stay together for the most part. But you've got to remember that protons are positively charged. And if you've got a whole bunch of positively charged things in a very, very small area or very, very small volume, you're going to start to experience some kind of repulsion between them. So what's going to happen is that there's going to have to be more neutrons in the nucleus in order to offset that electrostatic repulsion that's going to occur between positively charged particles in the nucleus. Just to give you a little bit of perspective onto how packed the nucleus actually is, I want you to think about the Raymond James Stadium. All right, imagine that's the size of an atom. Okay, so imagine the atom is Raymond James Stadium. If you were looking for the nucleus would be the size of a grain of rice in the middle of the football field. So the nucleus is the size of a grain of rice. The atom would be the size of the entire stadium. So what I'm talking about is a very, very densely packed nucleus here. So that's what happens. We add in more neutrons in order to make it more stable. Does anybody have any questions so far? Now, at some point, once we get to around 83 protons, it actually becomes impossible to have that number of protons in a nucleus and for it to be actually stable. There's just too many protons. That's kind of the point at which we have to say, well, we can't have that many protons in a nucleus and have any stable isotopes. It doesn't matter how many more extra neutrons we add in, it's still going to be unstable. So that's what we're finding with the periodic table as well. So if you take a look at the periodic table, we'll go back to it here. You'll notice that after we get past 83, we get these mass numbers, but they're all in parentheses. And these mass numbers then represent the mass of the most stable known isotope of these elements. But that's the point. After 83, you don't get any stable elements. So a lot of things end up decaying down to lead and bismuth, but mostly lead, because lead is incredibly stable. Lead 207 here being probably the most popular lead that we see around the place. But most of the lead that is in the world comes from radioactive decay of these bigger elements. All right, does anybody have any questions so far? Anybody have any questions so far? Okay, so what we're dealing with then is we've got this band of stability. So all of these dots here represent stable elements. Anything above or below those are going to tend to decay radioactively. And what we notice is that things above the band or above these dots in this area here where I'm pointing with the cursor above will tend to decay by what we call beta emission. And the ones below will tend to decay either by positron emission or electron capture. Both of those pretty much do the same thing. And then we've got a whole bunch of things that also are down here that will tend to decay by alpha emission. But that's more reserved for the very much more heavier elements. So let's take a look at what those kinds of emissions are. And I'll come back to why certain things decay by beta emission and certain things decay by, beta emission and certain other things decay by positron emission or electron capture. But we want to go through and look at these separately now. So as I said, the very much heavier elements, let me shrink this a little. That's better. The very much heavier elements will often decay with alpha decay. Now, alpha decay is loss essentially of a helium nucleus. So let's say we know, oops. Let's say we know that we have uranium-238. We know that it decays by alpha decay, and we want to figure out what it actually forms. This is how we do it. So we've got uranium-238. Now remember what this means. Uranium-238 means that when you're dealing with uranium and the mass number is 238, how do we know the atomic number? Well, the atomic number is real easy to figure out because we just go back to the periodic table, which obviously you'll have in front of you, and that will tell you the number of protons. Where are we? Oh, so it's the other. There we go. So uranium is down here, and you can see that the atomic number is 92. That's the number of protons. Now, it's optional because each of these actually uniquely defines an element. We don't need to put the 92 down here because we can easily get it off the periodic table. So often you won't even see the atomic number stated, but we know for uranium-238 that it would be 92, and that number can optionally be written. So it's optionally stated down at the bottom. So that is the atomic number of protons. And of course, the 238 is going to be the mass number, which we already agreed is equal to the number of protons plus the number of neutrons. So we can easily get the number of neutrons by subtracting the number of protons from the mass number. So 238 minus 92 will give us the number of neutrons involved. We don't really need to do that here, but I'm just pointing this out as to what this is showing. All right, let's see how you're feeling about this so far. Let's see. 5, 4, 3, 2, 1. All right, any questions? I mean, I know somebody's struggling here. Any questions? Okay. So uranium-238, and we're saying that it decays by alpha decay, which is loss of a helium nucleus, which is 4He. And the atomic number there is going to be 2. And again, we get that off the periodic table. So what we're looking for here is this mystery element, what I like to call the element of surprise. That's a Y there, by the way. Okay. And what we're trying to do is figure out what this element is, this mystery element that we're getting once it decays by alpha. So it's an alpha particle, that's alpha decay. And it's just really simple math here. So you can see that Y is going to equal 234. Z is going to equal 90. So the element there is going to be TH. And I know this because, oops, I don't want to go there, I go here. TH, there is, CTH has an atomic number of 90. And so that's how I know that this element here is going to be 234 TH. That's what goes in here. How do you all feel about the math on that? How do you all feel about the math on that?
Can you go back to the problem?
Okay. Oops. Can I go back to the problem? Yes, I can. Here we go. It's this one here, Katie. So what's your question?
So you figured out that it was because we had U-238.
Yeah.
And we knew that it was a helium nucleus, and we just subtracted the helium from the 238 to figure out what the other element was.
Yeah, because the whole point is that whatever's on the product side has to match whatever's on the reactant side. So, you know, for the addition of mass and everything on both top and bottom. Is that okay?
Yes.
Katie? Okay. Any other questions? Were you one of the ones who said I understand halfway, Katie?
Yeah, because I wasn't seeing.
Okay, that's okay. I just wanted to see if okay, so it's one person, and I'm just not sure what question they have. All right, let's talk about the next one, which is beta minus decay. Now, beta minus decay is loss of an electron. So let's talk about this. We've got calcium 46. And we know that it decays by loss of an electron. So let's see what an electron is. So electron has the symbol E for electron. The mass of an electron is 0, essentially 0 anyway. And the charge on an electron is -1. So that's where the -1 comes into play. Calcium has an atomic number of 20. So when we do the math here, we can see that Y is going to be 46. Z is going to be 21, not 20. 21 minus 1 is 20, right? 21 minus 1 is 20. And that would be SC if we look it up on the periodic table. Okay. How do you feel about that one? How do you feel about that one? 5, 4, 3, 2, 1. I suspect it's the same person who's understanding halfway here, but they're too shy to ask a question. So I don't know. I don't know how I can help really, unless a question is asked. So I'm not sure what the problem is. If you could enlighten me, I can help. Any questions? Okay. Let's say we're talking now about positron decay. Positron decay is loss of a positron. What is a positron? A positron is an antiparticle. It's the antiparticle of the electron. So I know this is really going to shock all of you, right? But I'm a bit of a Star Trek fan. Oh, I know, you're shocked. You're shocked. But anyways, they talk a lot about antimatter in there, and this is actually an example of antimatter. The positron is the antiparticle of the electron. If you take antimatter and matter of equal masses and you put them together, what happens is that they completely annihilate each other with the great release of energy. So that's how matter and antimatter are related to each other. So positrons. What are we doing with positrons? So we've got dysprosium, and we're trying to figure out this mystery element here. And a positron has the same symbol as an electron. The mass is 0, but the charge is exactly opposite. It's 1. It's positive 1. So this is an antiparticle. So the dysprosium, I can't remember the atomic number of that off the top of my head. But I go down here to the periodic table and find it. There it is, 66. So 66 goes here. And you can see that Z would be 65, which happens to be TB, and the mass would still be 154. All right, that's positron decay. How do you all feel about positron decay? How do you all feel about positron decay? 5, 4, 3, 2, 1, 0. All right. Everybody seems to be okay with that. The next one is called K electron capture. And K electron capture is something a little bit different. It's not actually the release of a particle, it's the absorption of a particle. So what happens is that K electron capture is actually the nucleus taking an electron from the very first row of the electrons, the very first energy level. So we know that down the bottom there's 2 electrons very close to the nucleus. They're the 1s electrons. So it's the removal or the absorption of these 1s electrons into the nucleus. So because it's an absorption and not a release per se, then the electron is actually on the reactant side. And that's how we can turn mercury here into what amounts to gold. So let's look at the atomic numbers here so you can see them. Mercury down here, so it's 80 and 79. So 80 on mercury and gold is 79. So that's the element we get out of that. So even the word capture is suggesting that it's not an electron that ends up being released, it's an electron that ends up being absorbed into the nucleus. Now, one thing I haven't covered yet, but I will cover pretty soon, is why certain things undergo beta emission and certain things undergo positron emission and certain things undergo electron capture. So there's a good reason why some go one way and some go the other. First of all, they're unstable and they want to be more stable, but there's a specific reason for why some of these go one way and some of them go the other. But we will get to that. All right, any questions about decay electron capture? The last one is called gamma decay, and you'll notice with gamma decay, it's simply the release of a very high energy photon. So this is used to lower the energy of the system, but what happens is there's no change in the mass or the atomic number here. So if you had 241 neptunium and it releases a gamma particle, it's still 241 neptunium, it's just that it has released energy in the form of a photon. Now, let me talk a little bit about these different kinds of radioactive decay and how we might defend against them if ever we're involved with them. Now, the alpha decay, as you can see, is helium. That's a pretty heavy particle. You can actually stop a helium particle with a piece of paper. So anything the thickness of a piece of paper will stop a helium particle from coming through. So that's why alpha alpha radiation is not incredibly dangerous. It actually can be stopped by the skin. So it's not awful. I mean, you'd have to actually ingest something in order to be harmed by alpha radiation. Beta radiation, though, that's the release of an electron. That's this one here, beta decay, is pretty dangerous because you can only stop that with 2 inches of lead. So unless you've got a 2-inch thick or 1 to 2 inch thick piece of lead between you and the beta emitter, then you're going to be in a little bit of trouble. That's because these electrons can get in and take electrons, push electrons off of DNA, and that's what causes DNA mutations, which leads to cancer. So, so beta decay is pretty dangerous. And the most dangerous, though, is gamma decay. You need about 6 feet of lead in order to stop a gamma ray. That's a very high energy photon, and that does the same thing, except it's kind of worse than these than beta decay, in my opinion, because of the how hard it is to stop that kind of radiation. So it's very high energy photons. You don't want to be exposed to those. All right. Does anybody have any questions? All right. Let's talk about the proton and neutron rich concept. I don't have notes about this. I do have a video about it. I'd recommend you watch that after especially if you don't understand what I'm going to be talking about now. I think it's best to show you the kind of question you're going to see on the test for this one. Let's have a look. Here we go. So you can see all these questions here. I'll go through them in a bit. Here we go. Damn, where are we? Here we go. So here's the question. An element has an atomic number of 41 and a mass number of 112. Using your determination as to whether or not it's proton or neutron rich, what is the atomic number of the element it becomes after radioactive decay? So that's what we're going to be talking about now, is looking at an element and being able to tell whether it has too many protons or too many neutrons. Okay, so what's the relevance of that? I go back up here to this graph that I was showing you earlier. And the contention that I'm making here is we've got neutrons on the y-axis and protons on the x-axis. So what I'm saying is that anything above the band of stability here, anything above the stable isotopes, is going to have too many neutrons. Anything below this line is going to have too many protons. That's something you have to understand. So let's see, how do you feel about my explanation about proton rich and neutron rich? 5, 4, 3, 2, 1, 0. All right. So any questions about what I mean by proton and neutron rich? Okay. So what we can do is we can look at our example here, and we're going to be able to tell, funnily enough, whether this is actually going to be proton or neutron rich. So let's have a look. So I said the atomic number is 41 and the mass number is 112. So let's take a look at the periodic table. We can figure out what that element is based on the information I've given. 41, that's NB. So this is the element we're actually talking about, NB112. Now looking at when we look at the periodic table, we look at NB and we can see that the one on the periodic table, if we ran around it, would be 93. So this is off the periodic table, 41, sorry, oops, 93, 41. NB. So this is periodic table. Now, if you remember what I said about isotopes earlier, that they're all adjusted for natural abundance. So what I'm positing here is that I would call this stable niobium, because chances are that anything that is stable is going to be pretty close to the mass of 93, which is pretty much what we're getting here off the periodic table. So that's stable there. Now, what I can do is I can do a little math here, and I can figure out how many protons, how many neutrons there are. So the number of protons here is going to be 43. And the number of neutrons we get by subtracting 41 from 93, which is going to be 52. So that's our stable version of NB. Now, this is the one we're actually trying to talk about here. The number of protons here is still 41. Sorry, that's what I meant to put 41 over here. Sorry about that. Number of protons is 41. And the number of protons here is still 41. The number of neutrons, though, is going to be 71. Once I do a little math here. So as you can see here, I would call this neutron rich, because it has more neutrons than it would have if it was supposed to be stable, and we know it's stable by getting it off the periodic table. All right, let's see how you feel about that. How do you feel about what I just said? About the whole neutron rich thing. How do you feel about it? 5, 4, 3, 2, 1. That's good. Everybody understands it. I like that. Okay. So what's that mean? Well, as I said earlier, let's go back to the slide I was showing you. That anything above this band has too many neutrons. That is, it's neutron rich. And my contention here is that neutron rich things will tend to decay via beta emission. So let's see why that might be. So what I'm going to do is show you the equation of how our neutron rich friends here will decay by beta emission. Now, beta emission is loss of an electron. So I'm going to try and figure out what we're going to get from that if we lose an electron. I'll explain why this matters in a minute, but an electron has 0 mass and -1 charge. So what that means is our element is going to be 42 and 112. And 42 is MO. Now, what you'll notice here is if you look at the 42 of MO here and you compare it to the stable one, it's a lot more closer. It's a lot closer than we were with NB. So the difference there, it's still neutron rich. So it could decay again if it wanted to. But you'll see that it's a bit closer to the atomic mass here than the other one was. So that's how we know it's getting a little bit more stable. But the other reason, which is kind of the more advanced reason that I want to discuss here, is that if something is releasing an electron, what it's effectively doing is turning a neutron into a proton plus an electron. So you can see that the atomic number is going up by 1. That means a proton's being added, but an electron is being released. So if you think about it, that would have been from the decay of a neutron into a proton plus an electron, which kind of makes sense. If it's neutron rich, it's going to want to get rid of neutrons. But if it's forming a proton, then it's getting even closer to that whole thing of it not being neutron rich anymore. That's the whole point. Okay, how do people feel about this? I don't think people will feel quite as good as they did previously, but we'll see. It can be a bit confusing. So how do you feel about the whole neutron rich here? 5, 4, 3, 2, 1, 0. Okay, so we've got two people understanding halfway here. Any questions?
Can you just repeat it again, what you said?
About the whole neutron rich thing?
Yeah.
Okay, so what's happening here is something is neutron rich. For neutrons are going to essentially decay into protons and electrons. So you think about protons being positively charged and electrons being negatively charged. So a neutron can decay into a proton plus an electron, which is how it gets rid of the neutrons and forms more protons, which is how it becomes less neutron rich. Is that clear, Katie?
And therefore more stable.
Yeah, that's right. Because what's going to happen is ultimately the whole point of this is that it's going to, whatever element we're talking about, is going to get closer to this band of stability by doing that. Do you see what I'm saying? If it was up here, for example, it gets a bit closer and that makes it more stable. Fewer neutrons. Is that okay?
Yes.
Okay, any other questions? All right, let's look at the opposite example where something is proton rich. And I'm just going to make something up here. I'm going to use this because I already have it. Okay. So let's say we've got NB80. Let's say our element is NB80. It's still got 41 protons, right? So we've got number of protons is 41. The number of neutrons, well, I've just made this up by the way, folks. It's not coming from anywhere specific. Number of neutrons is 39. So how do I know this is going to be proton rich? Well, it's a little bit more complicated than the previous one. But what I want you to see is that if something is neutron deficient, then really it's also proton rich. And that's what I want you to realize. In other words, it's got too many protons for its own good because it has fewer neutrons than it actually needs. And you remember what I said about neutrons, how neutrons are needed to stabilize the protons to make sure that they don't all fly apart because they're all positively charged. That's kind of what I'm getting at. Not enough neutrons means it's going to be not stable enough. And it's going to be considered to be proton rich. How do people feel about this so far? Does anybody have any questions? I'll do a poll at the end here. Okay. So if it's proton rich, what's going to happen is it's going to decay via positron decay. So let's have a look. So it's 80, 41, and it's going to decay into something plus a positron. Now positrons have a 1 here for the charge and 0 for the mass, so it's the opposite of the electron. And the element then would be 40 and 80. Now the element 40 we get off the periodic table, and that's going to be zirconium. So ZR is going to be the element here that we're going to get from positron decay. So what I'm talking about there is that a neutron here, remember the proton rich is going to mean that there's too many protons. So what can happen is a proton can decay into a neutron plus a positron. So if you think about a proton just being a neutron and a positron, then you can see that that's how we can get protons turned into neutrons, and it can get closer to stability that way. I'm not sure how people will feel about this one, but we'll see. How do you feel about this one, the whole proton rich thing? How do you feel about the whole proton rich thing? 5, 4, 3, 2, 1, 0. Okay. Any questions? Any questions? Any questions? All right. All right, let's go through some of these other questions that you're going to see here. We've got the question 1, which is calculate time required for a sample to remain. So it could be remain or decay. So you can see that there's examples of both of these here. They could both be remain, they could both be decay, or we could have one of each. That's what we're seeing here. I'll give you the formulas up here. See. An element has an atomic number of 76, a mass number of 128. This element undergoes alpha decay. The atomic number of the element formed is, and then the same question, but it's looking for the mass number. I'll do this as an example just to show you. So for 76, 128, you actually don't even really need the actual element to do this. You just need to know that an alpha particle is a helium nucleus. So I'm just going to call this X, but it isn't. But I could go find the element if I wanted to. Actually, I won't. Well, I shouldn't call it X. I guess I should call it. Something like Z, not even Z. Something that doesn't have Q. There we go. It's better. We'll call it Q, even though that doesn't exist. So we need to figure out what this is, and the atomic number then would be 74, and the mass number would be 124, and those would be the answers you'd be looking for both of these. Obviously, you're going to get different things happening on each, but that's how you'll do it. The mass number is on top, the atomic number is on the bottom. Does anybody have any questions about answering questions 3 and 4? Any questions? How do you feel about questions 3 and 4? How do you feel about questions 3 and 4? 5, 4, 3, 2, 1, 0. Okay, so everybody who voted understands it. All right, any questions? So then we've got the same thing for beta minus decay, which is also called beta decay. Beta plus decay is positron decay. It's the same thing. Then you've got your K electron capture and the gamma ray emission over here as well. So you go through each of those. It'll ask for the atomic number and the mass number, but it's always different numbers here. Question 13 is, again, it's just a math question essentially. So let's say we've got something like this where you've got these different elements. I'll show you how to do this. It's not really that difficult either. You'll notice I haven't included any of the atomic numbers here, but we don't really need them. So for this one, what we're looking for is the mass number of this element X. And we're told that we're getting 3 neutrons. Now, a neutron, if we were to include the atomic number, has the symbol N, and it has a charge of 0 because it's neutral, and it has a mass of 1. So that's where that comes into play. To do the math on this, it's this 227 plus 19 equals 83 plus X plus 3. So think of the neutrons here as 3 neutrons as being 1 neutron plus 1 neutron plus 1 neutron. So 3 neutrons here. And they each have a mass of 1, and there's 3 of them. So the total mass there is 3. Then we can just do some math to figure out what X is, and then we've got the value of X. Does anybody have any questions about that?
So we would just add up both sides and then subtract the.
That's right. Just don't get tricked up by the neutrons, right? By how many neutrons there are here. That's the only trap, I think. Does anybody have any questions? I don't even think I'll do a poll on this. It's one of those things, either you understand it or you don't. If you're not understanding, you should be asking a question right now.
So just to clarify, for the last part, for the neutrons, it would be X plus 3.
I'm sorry, could you repeat that, please?
For the last part, is it X plus 3?
Yeah, it's X plus 3, that's right. All right, any other questions? And then question 14 and 15 are the ones where we were talking about it being proton or neutron rich. So it could go either way on those as well, and then you can figure out the element based on what you're seeing here. As I said, there's no notes about this, but there is a video about it, and you'll find that video here in the mini lectures folder, and it is proton or neutron rich, this one here. That's the one I'd recommend you watch.
So basically, once we determine which element it is, if the mass number is less than what the true mass number is on the periodic table, then it's going to be proton rich. And
that's right.
Higher, it's going to be neutron.
That's exactly right, Katie.
And then that's how we're going to determine which one to use.
Which mode of decay to use, that's right, yeah. So if it's proton rich, and it makes sense, if it's proton rich, it's going to be positron decay. It wants to release positive charges, right? So, and if it's neutron rich, then it's beta decay, so it's releasing electrons. I think that makes some sense, I think. All right, any other questions? Well then, I think that's it for today. If anybody wants to hang around and talk to me, they can. Don't forget about the essay questions. Get them done sooner rather than later. The end of the semester creeps up very quickly, and you can find yourself having run out of time if you do not address these things in a timely fashion. Although I know that almost none of you will get them in early, maybe 2 or 3 of you will. I think that it would be well advised that you get the essays done as quickly as you possibly can. All right, does anybody have any questions? Okay, then I will see you all, well, I'll see some of you in a few minutes. I'll see the rest of you on Thursday. All right, have a good day.